Okay, let's dive right in. For all you engineers out there who work with motion control, I've got a question for you about a danger that's probably hiding in plain sight on your machines. Just think about it for a second. You've got this huge spinning load, a super fast gantry. What could possibly be more dangerous than that? Well, the answer might surprise you.
And right there, that is the fundamental, deep-down flaw of old-school machine safety. For decades, the philosophy was pretty simple. Something goes wrong, you smack the e-stop, a giant contactor clunks open, and it kills all the power. Problem solved, right? Well, not so fast.
This quote just nails it. That old brute force method didn't actually create a safe stop. It created an uncontrolled event. The system basically just threw its hands up and abdicated all responsibility at the most critical moment possible, leaving everything up to physics. And that, my friends, is a huge liability.
So this is where things had to change. This brings us into the modern world of functional safety, which is a complete 180-degree philosophical shift. The goal is no longer just about cutting energy. It's about intelligently guiding the machine into a predictable, known, and safe state.
Really, the hero of this story is the IEC 1658 standard from way back in 1998. This was the turning point. It established this core principle that for any single fault, the system itself has to be smart enough to prevent a disaster and transition to a known safe condition. This standard literally laid the groundwork for everything we have today.
And that groundwork eventually grew into a really specific standard just for drives, IEC 61800-5-2. Now, don't get bogged down by the acronyms here. I want you to think of this as a specialized set of tools in your engineering toolbox, where each tool is designed to solve a very specific problem. Let's pull out the most important ones.
So, let's start with the most fundamental tool, Safe Torque Off, or STO. This is the modern intelligent replacement for just yanking a contactor open. It instantly cuts the torque-producing current to the motor, and this is the absolute key, it leaves the drive itself powered up. And that allows for a crazy fast restart once the coast is clear.
Now, building on STO, we have two main ways to stop safely. Safe Stop 1, or SS1, tells the drive to ramp down to a controlled stop, and then it fires off STO, killing the torque. Safe Stop 2, SS2, also ramps the motor down, but instead of cutting power, it shifts into something called Safe Operating Stop. The crucial difference is what the drive does after it stops, because that's what dictates how quickly you can get back up and running. And this is where you really see the intelligent part of modern safety come to life. With Safe Operating Stop, the drive never lets go. The servo loop stays active, and it's holding that axis in position under full control. If it even senses the tiniest drift, it faults out. This is what allows an SS2 stop to restart almost instantly because the drive never actually lost its grip on the axis's position.
Okay, so stopping is one thing, but beyond that, we have this whole suite of monitoring functions. You've got safely limited speed, SLS, for when you don't want to stop, you just want to slow down for an operator. There's safely limited position, SLP, which basically creates virtual walls to protect your expensive tooling. Safe brake control, this is an absolute non-negotiable must-have for vertical axes to fight gravity. And safe direction, to make sure an axis doesn't suddenly decide to run away in the wrong direction.
All right, enough theory. That's great, but let's see how this toolkit actually solves the real problems that engineers like you are facing out on the factory floor every single day.
We're going to walk through 4 super common scenarios here. Each one shows how you match a specific safety function to a specific hazard. We'll start simple with a guard door, and then we'll move up to a collaborative robot, a vertical axis, and even a servo press.
First up, the classic guard door interlock. An operator opens the cage, the sensor trips. The drive immediately triggers STO, killing motor torque. But here's the beautiful part. The drive's brain stays on. The operator closes the door, hits reset, and production is back online in seconds, all without a full time-consuming power cycle. This is all about slashing that downtime.
Now for something a bit more sophisticated, a human-robot collaboration zone. When an operator steps into the work cell, you don't necessarily want to bring the entire machine to a screeching halt. Instead, you trigger safely limited speed. The robot just slows down to a verified safe creep speed. Production keeps rolling, just at a slower, safer pace. This is a perfect example of how safety can actually enable productivity, not kill it.
Okay, any vertical access. Using STO by itself here is a recipe for absolute disaster. The second you remove torque, gravity wins, every time. That's where safe brake control is critical.
You always pair it with STO to make sure that a fail-safe mechanical brake slams shut at the exact same moment the motor torque disappears, safely holding the load and preventing a freefall.
Now, all these functions are fantastic, but for a long time, they still required this separate, complex rat's nest of hard wiring. The next massive leap forward was integrating safety directly onto the motion control network itself. And the difference is just night and day. We go from these thick bundles of dedicated safety wiring to just sending safety signals over the same standard Ethernet cable that's already handling our motion profiles. We're talking about protocols like FSOE, which stands for Fail-Safe over EtherCAT. This is a total game changer. It shrinks your control cabinets, it lowers your bill of materials, and it makes safety zones something you can configure in software instead of with a pair of wire cutters.
But, this evolution didn't happen overnight. It's really been a 30-year journey, taking us all the way from clunky mechanical relays to these incredibly sophisticated integrated solutions.
Let's translate what these specs actually mean for you. SIL 3/PLE, that's the highest level of safety integrity you can get. It's for those applications where failure could have incredibly severe consequences. Category 4 means the system is designed to be tolerant of any single fault. And my favorite line on here? External relays, none required. That's the payoff for networked safety. The entire circuit is inside the drive, saving a massive amount of panel space and wiring headaches.
And this is the end result. A single, compact module that contains the entire safety toolkit we just talked about. 11 different functions, from the basic STO all the way up to advanced position and speed monitoring, all configured through software.
When you look at this timeline, you can really see the story unfold. We went from simple, brute force hardware to the big aha moment of functional safety in '98. Then we saw the first integrated function with STO pop up in the 2000s. And now we have complete network safety libraries all in a single package.
So this all leaves us with one final important question to think about for your own designs. With the tools we have available today, safety is no longer just a requirement you have to bolt on. When you implement it intelligently, it can slash downtime, increase flexibility, and actually improve your machine's throughput. So the real question is, which role is safety playing in your system?